Today we're going to look at something called piecewise function and something called one-sided limits. Now there are some functions that cannot be described with just one equation. In grade 12, those would be ones that they just gave you a picture of. You remember some of those pictures that was like a line, a line, a line? There's like three lines joined together. And they never gave you an equation, they just said, this is f of x, let's do something with it. Well, we could make an equation for that, but we'd have to make that equation in different pieces. And that's something called a piecewise function.
I'm so sorry to interrupt.
No problem.
Could you please ask Rhea Sager to come to the office with her things?
All right.
Thank you.
All right. Sounds good. So, for example, the most common piecewise function that's introduced to you early, the absolute value of x. Do you remember that from grade 12 being a graph that looks like this, a V-shaped graph? Now, technically, all an absolute value is two straight lines joined together. It is this one, if I draw this side in blue, that's just y equals x if it kept on going. And this side is just y equals negative x if it kept on going. So the way that we write a piecewise function, and the absolute value of x could be written this way, is we break it up and say, well, y could equal sometimes x, that's the blue one, maybe I'll write that in blue, but only when x is bigger than or equal to 0. And then we could say for the green one, the other time it's negative x when x is less than 0. It has two pieces. And check it out. If you plug in 5, you'd fall into this top part, and the answer would be 5. If you plugged in negative 3, it would fall into the bottom part, and you would have negative 3, which would make it positive 3, which makes it work out. So we could have written the absolute value of x as a piecewise function, or we can write it with the absolute value of ours because we've learned that symbol. But some functions have to be written in two different pieces. So here's our first one that we're going to look at. It's the half parabola, half line graph. One piece is a straight line, one piece is a parabola. So what would that look like? And if you're graphing these, again, I'm going to color code them here. I'm going to look at the 2x plus 1. I'm going to do that part in green. And I'm going to do the x squared part in blue. And I'm going to start by graphing them just with a faint dotted line. If you have a pencil, you can maybe do them first in pencil, and then we can color them in afterwards with their color. So 2x plus 1, that's y equals mx plus b. It has a line intercept of 1 and the slope of 2, so I go up 2 over 1, up 2 over 1, up 2 over 1. And it would look like this, as a dotted line for now. And if I go to my parabola, it's a regular parabola, over 1, up 1, over 1, up 3, over 1, up 5. That would be my parabola. Now, what we have in a piecewise function is the place where you switch from one piece to the other. In this case, it switches at 1. So what I'm going to do is on the green graph, I'm going to plug in 1. And 2 times 1 plus 1 would be 3. I would have on the green graph the point 1, 3. And I'm going to fill that in with a thick circle because there's an equal sign with the 1 on the green graph. On the blue graph, I'm going to label 1, 1, but there I'm going to label it with an open circle because the 1 wasn't included with the blue graph. Then to finish this graph, we just draw the appropriate piece. So for the green graph, it says only draw the green graph when x is bigger than or equal to 1. So that would be that section of my green graph. And for the blue graph, only draw it when x is less than 1. That would look like this. And so it's a graph that has two pieces. Can you see that this graph is still a function? You remember, you can test if something's a function with the vertical line test. And so it almost is not a function at 1, but one of the circles is open and one of them is filled, so it's still passing the vertical line test as it goes from left to right. Now in limits, we have regular limits, which is like the limit as x approaches 0. At 0, this graph is continuous. We would say the limit as x approaches 0 would be 0. At 4, the graph is continuous. We would say the limit as x gets close to 4 is none, because we can just plug those values in. But we have a problem in this graph that the limit as x approaches 1 does not exist. Because as I get close to 1 from the left, I get close to 1 as a y value. But as I get close to 1 from the right, I get close to 3 as a y value. So if coming from the left side and the right side is a different number, then we would say the limit doesn't exist. But sometimes to help show that, they've introduced something called a left-hand limit and a right-hand limit. Meaning that you come from the left side and see what it's equal to, you come from the right side and see what it's equal to. And we write that, from the left side we write a little negative with the number, from the right side we write a little positive with the number. So if I was coming from the left side, and I'll show this with, here I'm coming from the left side, I'm getting closer to 1, my y value would equal 1. That would be my left side limit. My right side limit is coming from this direction, getting closer to 1. That would equal 2. So if your left-hand limit and your right-hand limit don't equal, then we say the actual limit does not exist. If they are equal, then what they equal to will be the actual limit as well. So we have this statement here. If the limit from the left side does not equal the limit from the right side, then the limit doesn't work. If the limit from the left side is L, and that's the same as the limit from the right side, then we can say the actual limit at that value is also L. So if we're finding a limit, and in this case we're going to graph it as well to practice graphing these piecewise functions. Sometimes what people like to do when they're graphing is they like to start with the point. So if I plug in 2, because that's where things are changing, and again I'm going to do the top part in green. 3 times 2 minus 2 is 4. So I have the point 2 comma 4, and since there's an equal sign, that dot would be filled in. When x is less than 2, I would plug that into the blue one. 2 squared is still 4. That would be an open circle, but can you see that that's right on top of the filled-in circle of the other? So we have the point 2 comma 4 on the blue graph and the green graph. Now when graphing the green one, 3x minus 2, that would have a y-intercept of minus 2 and a slope of 3. I'm just writing some dots here with my slope. But which part am I going to graph of the green one? I'm just graphing this section when it's bigger than 2. With the blue graph, I've got an x squared graph. That would have these points. And now I'm only graphing this part right here. So this one, even though there's 2 pieces, this graph, we would say, is continuous. The last one was discontinuous. And remember, the question is, could I draw the whole thing without lifting my pencil? Yes. Because even where it breaks to the new part, that point is the same on each one. So you could just continue. So now, if we were trying to find the limit as x goes to 2, can you see that it is equal to 4? Because if I go from the left side and I come from the right side, both values come to the same thing. It's going to equal 4. Find the limit if it exists. So now we've got 5x plus 5 when x is greater than or equal to 2. So if I plug in 2 in that case, I'm going to get 2 comma 15. And if I plug in 2 into the other graph, I'm going to get 2 comma 7. Five x plus 5. We would have that part of the line. X cubed minus 1. There's your x cubed graph, just translated 1 unit down. And if we come from the left side and we come from the right side, we go to different numbers. The left-hand limit would be 7. The right-hand limit would be 15. And since those numbers are different, we say that the limit does not exist. Anytime that there's a limit that does not exist, that means there's some sort of break in your graph. In this case, you would not be able to draw this whole thing without lifting your pencil. You'd have to lift it up and connect it at the other part. Mathematicians, we are notorious for not liking to write lots of things down. So as soon as something seems like way too many letters, we come up with something shorter. So there is does not exist. Let's just go with DME. Nice and short. Okay? Like x belongs to all the real numbers, we got that down to 3 funny, like all the x is normal, but then a funny e, and then a funny r, but then it's shorter, right? Here are some of my favorite shorthand things in mathematics. The upside down A. This replaces having to write for all, because that would take so long, right? But sometimes you're working on a proof, and you say, it works for all x belonging to the real numbers, so then you could end your proof by just having, like, that at the end. And then another thing that comes up in proofs that I really like is this one. If, in mathematics, this stands for if, and only if. Which is kind of a funny, like, it's not just if this happens, but it's if and only if this happens. Like, it's really important that it's only this happening. Then you can write if with an extra f, and it stands for if and only if. So, which, I mean, it can shorten something down. Like, you could say that x minus 3 is, oh, no. I'm trying to think of a nice. X squared minus 1 is greater than 0. No, I'll come up with something. But there's some fun shorthand versions for now. Other ways of looking at limits. Here's a pattern. Can you fill in the next 3 blanks of the pattern? It's not supposed to be crazy. Okay? How'd you do? Did you get that the next one was 0.2222, and then 0.22222, and then 0.2222222? And if you kept going on forever, would the last number be 3? No. Or, well, there's no last number, but if you kept on going forever, can you see we just add more and more 2's? So now we want to imagine doing this forever, for infinity. What would it get closer and closer and closer and closer to? Right? So, what would be another way that you would write that? Because that's what it would keep getting closer, or you just keep getting more and more 2's, right? Mathematically, when you had something like this show up on your calculator, and you wanted to write it down on a quiz or a test, and you didn't want to round it, what would you write? So you ever do a line over top? Do some people do a dot over top? A repeating decimal. Yeah, what do you call it in French? So it just keeps on going. Now, this is actually a number. I don't know if you remember, this is going back to grade 9, but grade 9, you learned that rational numbers were numbers that could be written as fractions. And rational numbers included decimals that repeated themselves. So this decimal that repeats itself is actually a fraction. Does anybody know what fraction would give you, if you typed in 1 over 4, I get 0.25. Well, that was close, but it's not 0.2 repeated.
2 over 9.
2 over 9. And so this sequence would get closer and closer to 2 over 9. Did you know that 1 over 9 was 0.1 repeated? Oh. 1 over 9, anything over 9 is that number repeated. So 1 over 9. Did you know 3 over 9, which is 1 over 3, did you know 1 over 3 was 0.3 repeated? And 1 over, or 4 over 9 would be 0.4 repeated. And now we get to play with your mind just a little. Which is bigger? 0.9 repeated or 1? What would your gut say? 1. Good. That's what you normally should say. Unfortunately, that is not right. You would think that 1 would be bigger than 0.9 repeated, but actually, these are the same number, which is really weird. Now, my hope right now is to show you that they're the same number, starting with the least convincing argument to the most convincing argument. My least convincing argument is this. Since 1 over 9 is 0.1 repeated, and 2 over 9 is 0.2 repeated, and 3 over 9 is 0.3 repeated, it must be that 9 over 9 is 0.9 repeated. And most people would go, no, 9 over 9 is 1. I'm not going to agree with you there. But that's my first argument. Just looking at the pattern. If 3 over 9 is 0.3 repeated, 7 over 9 is 0.7 repeated, why shouldn't 9 over 9 be 0.9 repeated? But I could also maybe convince you by, most people are fine that 1/3 is 0.3 repeated. And another 1/3 would be another 0.3 repeated. And another 1/3 would be another 0.3 repeated. And if I added this side, 1/3 plus 1/3 plus 1/3, you'd have no problem saying that that's equal to 1. But if I go to my decimals and I add them up, I never have to carry over a 1. Because all those 3's are lined up. Every column will always add up to 9. Forever. And you never have to carry something over. So I think this is a little bit more convincing that 0.9 repeated and 1 are the same number. And finally, I'm going to do a little proof using algebra. We're going to start off by saying x is equal to 0.9 repeated. And since this is equal to each other, what I could do is I could multiply both sides by 10. So then 10x's, well, that would just move my decimal place over, would be 9.9 repeated. Because the 9's would all move over one decimal, but since they're going on forever, this is what I would have. And if I now, on this side I use my algebra, and I subtract x, and on this side I use my decimals, and because I subtracted x on one side, I'm going to have to subtract x on the other side. If I do that, then wouldn't all the 0.9 repeateds go away? This side would just equal 9. This side would equal 9x. If I divide both sides by 9, I find out that x is equal to 1. But I started off with x is equal to 0.9 repeated, and I got x is equal to 1. And they are, weirdly, the same number. Mathematically, if two numbers are different, there's always a number in between them. You can always find smaller, more decimals, something in between. There is no numbers in between 0.9 repeated and 1. And since there are no numbers in between them, they are considered the same. Now, I'm not saying that from now on in your science classes, the answer is 5, you write 4.9 repeated and see what your teacher does. That, you know, could be problematic. But technically, those numbers are the same. So there's some weird math for the day. So now we talked about continuous as a definition where you can draw a graph without lifting your pencil. But now we can talk about continuous from a limit perspective. If the limit as you get close to a value is actually the value, then we say the graph is continuous at that point. So for example, here's x squared. You have the point right? You have the point 2, 4. That means when I plug in 2, I get 4. That would be the f of a. Plugging in 2 gives me 4. The limit, as I get close to 2, from the left side, obviously, and from the right side, is also equal to 4. So if the point exists, and the limit is going to that point from both sides, in mathematics, this is the mathematical definition of what it means to continue, to be continuous. And continuity is really important for calculus and figuring out things going on, because if graphs break up, then we can't figure out the mathematics behind it. But if the graph is acting like we want it to, then we can figure out a lot of things about it mathematically at that point. So this means 3 things. If f is continuous at a, the actual point works. There's not a hole in the graph. So that f of a is defined, meaning it's not a hole. Maybe I can write that down. It's not a hole, or it's not a non-permissible value. It actually exists. The limit exists. So that means it's possible from the left side and the right side to be the same thing. And the limit is always going to equal that point. And we say that if f is not continuous at a, there's a non-permissible value or a hole, then we say that it is discontinuous at a, or there is a discontinuity. So here we have a piecewise function with 3 pieces. So I'm going to color code this with 3 colors. We're going to graph the top one in green, minus 3, when x is less than or equal to -1. It's equal to 2x between -1 and 1, and it's equal to +3 if x is bigger than 1. So first of all, when a graph is just equal to a value, y equals -3, that will be a horizontal line. So I'm going to start with my green graph. I need to draw a horizontal line at -3. I'm going to have a closed circle here. And I'm just drawing the horizontal line when x is less than or equal to 1. So I have the point -1, -3. 2x is a straight line. the y-intercept of 0 and a slope of 2. So I draw some points on there. And I would have an open circle at -1, -2, and an open circle at 1, 2. And I just have the straight line in between those 2 points with open circles because there's no equal signs with the 1s there. And then in purple, it's equal to 3. After that. So we want to find the following limit. Some of them are left-hand and right-hand side limits. Some of them are actual limits. So the limit, as you go to -1 from the left-hand side. Take out my yellow pen here. If I'm coming -1 from the left, I would be on this graph going this way. If I did that, I would end up at -3. That limit exists. To the left side limit, you just need to come from one direction. If I'm coming from the right-hand side, take out my yellow pen, -1 from the right-hand side, so I go to the right of -1 and I go towards it, that would be going in this direction. That limit exists. It would equal -2. So when we're evaluating a limit, we're trying to find the y value as we get close to a certain x value. If we go to +1 from the left-hand side, that would be this arrow heading in that direction. That would equal 2. And finally, if we were going to 1 from the right-hand side, that would equal 3. And so each of these they each exist because we're just coming from one side, okay? Where is f discontinuous? The graph jumps when x is -1, and the graph jumps again when x is +1. So we would say that is where the graph is discontinuous. So now what we have to do as our brain is we have to ask what is being asked of us in each of these questions. F of -4 is just asking if you plugged in -4, what would you get? So I go to -4, I look at my graph, there's a hole in the graph. So if I plugged in -4, I would get nothing. We've labeled the hole, but as far as the actual value, that one does not exist. If I go from -4 from the left-hand side, can you see that you are getting close to 2? -4 from the right-hand side, close to 2. And since the left side and the right side are the same, then we would say the limit also gets close to 2. For E, can we figure out f of 1? Well, there's a hole here and a filled-in dot there, so we would say that f of 1 is 4. It exists. If we go from 1 from the left side, we'd be on this graph on the left side, we'd be getting close to 4. If we go to 1 from the right side, we would be on this other piece of the graph, and we'd be getting close to -2. And we would say the limit does not exist. Because from the left and the right, they're different. Here's a weird thing. What is f of 6? Is it on the graph? Yes. It's equal to 2. But if you were approaching 6 from the left side, you'd be on this graph, and you'd be getting really close to 5. And if you approached 6 from the right side, still be on the same graph, you would also be close to 5. And we would say, okay, now what do we do with the limit? It's actually equal to 2. You can plug in 6, you get 2. What is the limit as x gets close to 6 then? Should it be 2, which is the actual number, or should it be 5, because that's the limit, or should it not exist because those things go against you? And the answer is 5. Because from the left and from the right, you're getting closer to 5. So no matter how, as you get closer and closer, you will keep getting closer and closer to 5, even though it exists somewhere else. Where does this happen in real life, a graph that would have something like this? Here's a real life example of something like this happening. Tickets for the zoo cost, and they're expensive now, aren't they? How much does it cost for the zoo? $15, $20? Yeah. Tickets to the zoo cost $20 each. So 1 ticket would be $20, 2 tickets, $40, 3 tickets, $60. And that would make a really nice straight line. Okay? But they might have a special on that says, if you buy 10 tickets, you can get them for $150. So all of a sudden there's a break in the graph because the pattern stopped. And you're like, no, I don't want to take advantage of that deal. 10 tickets for $150. There's only 9 of us. We will pay $180. Take advantage of the deal, right? But sometimes there's specials, and if you wanted to graph that special, well, things were working nicely on your graph at $20 a ticket, and all of a sudden you have a break. Now you can't actually buy close to 10 tickets. Well, what if I buy 9.999 tickets? It'd be like, no. There are some things, in fact, the example that I gave would actually have dots instead of a straight line, because you can't buy 9.5 tickets. But you could, if you were at a store, you could charge $5 a pound for chocolate chips. I don't know, is that a good deal? I don't want some chocolate chips right now. It's a bad example. You could charge that, and you could say, if you buy exactly 10 pounds, it's free. And the people get all excited, they fill their whole bag up with like that, a lot of chocolate chips, close to 10 pounds. They put it on there, and you're like, oh, 9.998. You add one more. Oh, it's 10.02. It'd be almost impossible to get exactly 10. But you have people filling up bags because the 10 pounds is free. Okay, so I have a worksheet for you. And we can actually start working on this. There's also textbook questions, so once again, you might prefer to work on the worksheet just because it's less cumbersome than the textbook. And the recommendation is to either, A, maybe you want to find a partner and work on them up at the boards. Maybe you just want to work with somebody close by, but it's more fun to work on this with somebody than it is without. Or if you like, you can work on your own. Okay, so we have 15 minutes to get as much done as possible.